All right, we are on homework number 30. First problem says find dy dx. So remember, when x and y are parametric equations, dy dx just equals dy dt, the derivative of y with respect to t, over dx dt, or y prime over x prime. All right, so dy dx, the derivative of y should just be negative 6. The derivative of x would be 2t. So I'll simplify it to negative 3 over t. For the next one, same idea. So start with dy dt. The derivative of e to the u is e to the u times u prime. So don't forget to take the derivative of this. So that's negative 1/2. Here it's 2e to the theta times 1 technically. Let's clean this up a little bit. So the negative 1/2 can come down here. Now if I bring a 2 down here times the other 2, that's a 4. And then what about the e's? So if you have e to the negative theta over e to the theta, you're just, remember, you're subtracting your exponents. So negative theta over 2 minus theta is negative 3 theta over 2, negative 1/2. So that just makes this negative 1 on top and 4e to the 3 theta over 2 on the bottom. If the question is just saying what's dy dx, it's not a big deal to leave it unsimplified. But if you're supposed to work with dy dx, set it equal to 0 or undefined, we need to be able to simplify like that. All right, for the next one, now we're finding dy dx and the second derivative. Find the slope and concavity if possible at the given value. So if possible, it could be that there's a vertical slope, so no solution, or it could be that there's no concavity. Maybe it's an inflection point or something, or linear. All right, so let's see. We're starting with dy dx. So dy dx is just 3 over 4. So I don't need to simplify that. And that means that the slope is also just 3 over 4. But if you want official notation, it would be like, when I evaluate dy dx at t equals 3, no matter what t is, it's always equal to 3/4. All right, so there's dy dx and the slope for that first one. The second derivative, just to practice the formula, remember it's the derivative with respect to t of dy dx divided by dx dt. So I think it's a good idea as you're first starting out to write this formula out each time so that when it's something more complicated, you have this in your mind. So the derivative of 3/4 is 0. Dx dt was just 4. Either way, that comes out to 0. So because the second derivative is equal to 0, that means we have no concavity, right? Because we need a positive number for concave up and we need a negative number for concave down. So in this case, no concavity. In this case, it's because if we were to graph xy, we would get something linear. So lines have no concavity. But like I said, it could have also been an inflection point for another reason that you would have no concavity at that changeover. All right, what's our next one? So let's start with dy dx. dy is just 4. Dx is 2t plus 5. And there's nothing to simplify there. The slope is what we get when we evaluate dy dx at t equals 0 for this one. So that would be 4 over 0 plus 5, so 4/5. So we get a slope of 4/5, and this was my answer for dy dx. For the second derivative, again, it's the derivative with respect to t of dy dx. So, and you know what? I'm going to rewrite this. I don't want to do quotient rule, so I want to rewrite this. I want to use power rule with a little chain rule thrown in. So the derivative of what I just got divided by dx dt. All right, so first let's do this derivative. So this becomes negative 4, 2t plus 5 to the negative 2. And we have to chain rule. The derivative of 2t plus 5 is 2. Clean that up later. And the derivative of dx dt was 2t plus 5. Right, so we can clean this up a bit. So this can multiply to negative 8. And this is to the negative 2. So I can bring this expression down. And it would get multiplied by the 2t plus 5 that's already down there. So we should have a total of 2t plus 5 to the third power in the denominator. So there's our equation for our second derivative. And then we are supposed to evaluate this at t equals 0. So that would be negative 8 over 5 to the third. Because this derivative, second derivative, is less than 0, then the graph is concave down at t equals 0. So second derivative equation, conclusion at t equals 0. Right? Let's look at number 10. Same instructions. So we're going to start with finding dy dx. So dy is 3 cosine theta. dx d theta is negative sine theta. And I'm going to make that negative 3 cotangent theta. You don't have to do that, but if I want to plug something into it, I just think that's easier than figuring out cosine over sine and all that. Evaluated at theta equals 0. All right, so negative 3 times cotangent of 0. Now, the cotangent of 0 is undefined. Cotangent has its asymptotes at 0 and pi, and tangent is at pi over 2 and 3 pi over 2. So this is no solution. It means that there's no slope. It's probably a vertical slope. If I had to graph this, we had something like this in our notes. This is probably an ellipse, right? If x equals cosine and y equals sine and there's a number in front. So yeah, we're probably at the end of the ellipse, so vertical slope. They don't ask for that specifically, so you don't have to get into all of that, but I'm just kind of explaining what's happening here. All right, the second derivative is going to be the derivative with respect to theta of negative 3 cotangent. Cotangent and tangent, I do not have those. Oh, no, wait, I do. Sorry, I'm thinking of integration. I was about to say I don't have those memorized, but I do have this memorized. That's another advantage of changing this to cotangent so that you're not doing quotient rule. Instead, you're just doing the derivative of cotangent. All right, so I set this up. The derivative of cotangent is negative cosecant squared theta. And then dx dt was negative sine theta. So we have 3 negatives happening here. So my result is still going to be negative. There's still a 3 out here. And cosecant squared over sine, that's the same as having sine cubed in the denominator, or you can make it cosecant to the third in the numerator. I need to evaluate the second derivative at theta equals 0. Now, sine of 0 is 0. So this is undefined as well. So there's no concavity. No slope, no concavity. Why do I keep doing that? No concavity, not no cavity. All right. So circle that as my conclusion there. Circle that as my answer. Okay. All right. Next section. Find an equation of the tangent line at each given point on the curve. So see how they give us 3 points here? We need to find dy dx at each of those. All right, so the first thing I want to do is, let's just start with the first one here. So we've got this point, negative 2 over radical 3, 3 over 2. And I can go ahead and find dy dx because I want slope. So here's y. So dy d theta is going to be 4 sine theta cosine theta. And derivative of cotangent is negative cosecant squared theta. So dy dx is, just to clean this up a bit, 4 divided by negative 2 is negative 2. We would have sine to the third if I bring those up. times cosine theta. All right. How do I know what to evaluate this at? I don't yet. I need to set one of my equations equal to, and I can choose either one. I need to set these equal to their x and y equations. So like -2 over radical 3, the x coordinate, is supposed to equal 2 cotangent theta. And if I'm trying to solve a trig equation, I get the trig part by itself. So divide by 2. All right, now you might have to think a bit on your unit circle stuff. Remember, here's the pi over 6 coordinate. Pi over 3, just flip them. All right, so cotangent is the x over the y coordinate. So as far as reference angles go, the x coordinate with a 1 on top is pi over 3, and the y coordinate has radical 3. So my reference angle is pi over 3. Cotangent is negative in quadrants 2 and 4. We can there are two ways to look at this. We can see that we're in quadrant 2 right here, right? Or we could say, yeah, this is when the x is negative and the y is positive. But we're definitely in quadrant 2. So what is the pi over 3 angle in quadrant 2? It is 2 pi over 3. I could have also used like negative pi over 3. I could have also used 5 pi over 3. It's not going to matter because the behavior of sine and cosine is going to be the same as you're doing. Like the signs that come out, the pluses and minuses, are going to work the same way. In this quadrant, sine's negative, cosine's positive, and this one, sine's negative, cosine's positive. I think I just said that backwards. But anyway, I'm going to use 2 pi over 3. I think on the key that I printed, I did like negative pi over 3. It just doesn't matter. All right, so -2 times sine of 2 pi over 3 is radical 3 over 2, and then we're cubing that. Cosine of 2 pi over 3 is -1/2. So this comes out to, let's see, those 2's are going to cancel. It'll be positive. Radical 3 to the third would be like 3 radical 3 over 2. Right? Okay. Oh, wait. Over 8. I can't cancel with that one. I can cancel with this one. This is 2 to the third, though. So that's 8. Okay, so I have my slope. I have my point. Y minus 3 over 2 equals the slope times x minus negative, so plus 2 over radical 3. Okay, that took a little while to get there. Now, I can use the picture to my advantage a bit. This definitely is a horizontal tangent. So when the point is 0, 2, I can see that the slope is just 0. So let's not do a bunch of calculus. Let's just say, okay, that's the horizontal line, y equals 2, because that's the y coordinate it goes through. Save ourselves some time on that. And then what about this one? So I already have dy dx. I don't have to do that again. But I do need to know when the point is 2 radical 3 and then 1/2. I need to know what the theta is. So again, I can say 2 cotangent theta equals 2 radical 3. And cotangent theta would just equal radical 3 if I divide by 2. And so what's the theta that makes that happen? So before, when we had 1 over radical 3, the angle was a pi over 3 angle. So now it's a pi over 6. Again, I can see that I'm in quadrant 1. I could also pick, what is it, quadrant 3, 7 pi over 6. It doesn't matter because you're going to get the same positive and negative signs throughout. So just pick either one of those. So I want to evaluate dy dx at theta equals pi over 6. All right, so back to dy dx. That was here. -2 times sine cubed. Sine of pi over 6 is 1/2 to the third. Cosine is radical 3 over 2. Even if I were in quadrant 3, these would both be negative, so I'm going to get the same sign anyway. All right, so this 2 can cancel with this one. There's still a negative. There's a radical 3. 1/2 cubed is 1/8, so there's that slope. And the equation would be y minus 1/2 equals the slope times x minus 2 radical 3. All right, so that was a long problem. Let's take a look at the next one. Let's see. Find all points, if any, of horizontal and vertical tangency to the curve. Use a graphing utility to confirm. I'm not going to do the graphing utility thing. We're not required to do that on the AP test, and I don't want to take extra time on this video as I'm running out of it. So, tangents. These rely on dy dx, right? So first let's find dy dx. We're talking about slopes, so we need a slope formula. So dy is 2t, dx is -1. So dy dx is just -2t. So let's say we start with, it doesn't matter what order you go in, let's say we start with a horizontal tangent. All right, a horizontal tangent happens when dy dx is equal to 0. We did this back in chapter 3, right? What makes dy dx equal to 0? When -2t is equal to 0. That would be when t equals 0. Okay, so what is a point of horizontal tangency? So points mean find the xy. So now you just need to calculate what's x of 0 and what's y of 0. X of 0 is 4. Y of 0 is 0. So there's a horizontal tangent at the ordered pair 4, 0. All right. What about a vertical tangent? Vertical tangent happens when dy dx is equal to undefined, which is when its denominator is undefined, but there's no solution to that. So there are no vertical tangents. All right, number 35. So same thing, let's find dy dx. So dy would just be cosine theta. Dx would be -3 sine theta. So dy dx, actually I'm just going to leave it like that because I could change it to -1/3 times cotangent, but I'm just trying to solve when each of these is equal to 0, so maybe it's nicer to have it as a fraction. Let's do horizontal tangents first. So horizontal tangent when dy dx equals 0. So when you have a rational expression, that's just when the numerator equals 0, keeping in mind that the denominator cannot equal 0 at the same time. And when does cosine equal 0? So I always go from 0 to 2 pi for these so that I can find 2 points. If you go past that, you usually start, say this is an ellipse or something. Once you get around 2 pi, you usually start looping back on yourself. So, yeah, so I'm not going to find, I always just find my 0 to 2 pi angles. All right, so theta equals pi over 2 and 3 pi over 2. So we need to plug those in separately. So I want to know what's x of pi over 2 and y of pi over 2, because that will give me 1 point. And then I'll do the same for 3 pi over 2. So x is 5 plus 3. Cosine of pi over 2 is 0. So x is 5. Y is -2 plus the sine of pi over 2 is 1. So that's -1. So this point, there's a horizontal tangent at 5, -1. And then we also need to do x of 3 pi over 2 and y of 3 pi over 2. So x will be 5 plus 3 times still 0. Y will be -2 plus sine of 3 pi over 2 is -1. So that's -3. So there's also a horizontal tangent at 5, -3. If you wanted to use your calculator to confirm these, you would just graph it. You change to parametric mode and type in these two equations. But sometimes the zooming is weird on that, so maybe you could also use Desmos probably. All right, what about vertical tangent? Vertical tangent when dy dx is undefined. And in this case, that would be when -3 sine theta, you don't need the -3, but you can, is equal to 0. That's really just when sine theta equals 0. And that happens when theta equals 0 and pi. So I need to find x of 0 and y of 0. So x of 0 is 5 plus 3 times cosine of 0 is 1. So that's 8. Sine of 0 is y of 0 is negative 2 plus sine of 0, which is negative 2. So one ordered pair is 8, negative 2. X of pi, y of pi. So x of pi is 5 plus 3 times the cosine of pi is negative 1. That's 2. Y will be negative 2 plus 0, which is negative 2. So 2, negative 2 is my my two vertical tangent points here. For 39, this says determine the intervals on which the curve is concave down or concave up. So concavity is based on second derivative, right? So let's get our first derivative so that we can get our second. First derivative is 3t squared minus 1 over 6t. And I just realized I just found a mistake in my key for 39. So, okay. So, because I saw this as a 1. All right, so this is dy dx. Now let's go into, now I could divide this out because I'm about to turn around and take the derivative of this. So my options are, do I quotient rule this thing? Or usually I said, no, don't quotient rule. If you just have a monomial, use our little heart trick. Make it 3t squared over 6t, so that's t over 2, minus 1 over 6t. That'll be easier to take the derivative of, because that's just power rule for both of those. Over dx dt. All right, so what is this derivative? This is 1/2, and then this is 1/6 times t to the negative first. So that's going to become positive 1/6 t squared in the denominator over, what was this? This was 6t. All right, so we have a little math to do here. Let's see, so common denominator there is 6t squared. So this needs to get multiplied by 3t squared, I mean. So that's going to be 3t squared plus 1 over 6t squared times 1 over 6t. Okay. Nothing exciting cancels. We have 3t squared plus 1 over 36t to the third. That's my second derivative. All right, now what about concavity? So we need to get our possible inflection points, which are places where the second derivative equals 0 or undefined. Now 3t squared plus 1 is never equal to 0 unless you're going to work with imaginaries, so we get nothing from there. 36t cubed is equal to 0 when t equals 0. That's pretty easy to toss on the number line, right? And you're testing into the second derivative. And remember, the top here, 3t squared plus 1 is always positive. So when you plug in negative 1, for example, you get this positive over negative 36. So that's negative. And if you plug in 1, you're going to get a positive over positive 36. Positive. So concave down, concave up. So you can say from negative infinity to 0, or for t less than 0, the curve is concave down. And for t greater than 0, concave up. I'm not including 0 in any of those because 0 is an inflection point, and there's no concavity at the point of inflection. All right, I think that finishes this assignment. So come into office hours if you have any questions on this, and we'll keep going on.